Boldly going where no science show has gone before. The Naked Scientists.
On The Naked Scientists this week, how fish use secret ultraviolet face markings to tell friend from foe, a trick to modify mosquitoes that could keep dengue fever grounded by making sure the females can't fly, and new fossil evidence of gigantic sharks in Cretaceous seas. But rather than terrorising the oceans, they munched on shellfish on the sea floor. I'm Ben Valsler, and joining me this week is Helen Scales.
Thanks, Ben. Also this week, we're looking at the scientific issues surrounding water. We'll be finding out how a pressure monitoring technique can help to reduce the strain on our water pipes and reduce some of the 32 billion cubic metres of clean water that are lost through leaky pipes every year. Plus, we'll be finding out how building a dam can change the local weather. Ben.
Thanks, Helen. We'll also hear about new networks in Africa and Europe that bring together researchers to better understand how we use water, how to provide water to those that need it, and how changes in our land use or in the climate will affect water security worldwide. And of course, Dave and I explore the science of water pressure in a very, very wet kitchen science.
That's all to come up today on The Naked Scientists. If you want to get in touch with any questions or comments, we'd love to hear from you. Just tweet at Naked Scientists or send us an email. The address is chris@thenakedscientists.com.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now this is The Naked Scientists with me, Ben Valsler.
And I'm Helen Scales, and I'm going to kick things off this week with a story about one of my favourite places to be, and that is on a coral reef. Now, anyone else who's been lucky enough to visit one will know that they come packed with colourful creatures and colourful fish. And now a new study reveals that some of those fish send out private messages using patterns of ultraviolet light that us humans and many other animals can't see. Well, it can be very important for fish to be able to tell the difference between different species, especially when it comes to damselfish. These feisty tiddlers defend their farms of seaweed from intruders, and the worst kind of intruder is a member of the same species, because they can come along and strongly compete for food and mates. Now, Ulrika Siebeck from the University of Queensland in Australia led a team of researchers with the enviable task of studying two species of damselfish on the Great Barrier Reef. And they've discovered that the Ambon damselfish, a small yellow fish, can read secret facial patterns of UV spots and stripes to tell one species from another.
Is it not obvious? Are there not big, gross morphological differences between one species and another?
No, these two actually, certainly to a human eye, look very similar. Really, I think we'd have a tough time telling them apart. If you got it under a microscope, you'd be able to pick it out. But essentially, the colour in our visual range is very similar. What the team did was they presented a wild Ambon damselfish with two other damselfish inside clear plastic tubes. This was in the wild on the reef. One of them was the same species, and the other one was this other species, the lemon damselfish. And under normal light conditions, the Ambon damselfish is preferred attacking other Ambons, so racing towards them and saying, you know, off you go. And if you've ever seen a damselfish in the wild, you'll know they are quite feisty for their size. They think they can take on divers, which is quite fun. Anyway, what they also did was they put these fish inside plastic tubes that blocked UV light so that those UV patterns weren't visible to the fish. And when that happened, they had no preference for a fish of the same species or of the other species, showing that it probably is quite important to be able to see UV. They also went into the lab and trained these damselfish using food rewards to distinguish between drawings of these UV face patterns. So really, together, these findings indicate that these Ambon damselfish can see these intricate UV patterns, and they probably use them to recognise faces of other fishes. UV makes a really ideal secret signal because not many other fish can actually see it. It's got a very short wavelength, which means it's quite easily scattered in water, making it actually not that useful for very precise vision, certainly over a longer distance. And very long-lived predators often actually protect their eyes from UV damage. That's what we do a lot with our eyes, and we screen out a lot of the UV. And this means that damselfish fish can communicate with each other, find mates, and warn each other to keep their distance without ruining that camouflage against predators, because the predators can't see it. And next, the team want to dive deeper into the UV vision of various fish to find out how far they can see, and perhaps to see whether they can distinguish not just between different species, but also between individual fish as well. And wouldn't that be wonderful? You could see your mate across the reef based on the patterns on his face.
There's quite a number of fish that take advantage of the fact that other species see slightly different range of the spectrum, aren't there? Because deep sea fish use essentially red light as an invisible flashlight.
That's right. That's really why the sea is blue, because the red light gets absorbed very quickly. So if you can emit or detect red light, you've got a really great secret wavelength as well. So yes, take advantage of the secret signals and you can do very well.
Now, researchers in Oxford and California have found a way to stop mosquitoes from growing wings, keeping them grounded and stopping the spread of diseases like dengue fever. Writing in the journal PNAS, Luke Alfie and colleagues highlight how controlling the principal vector, in this case the Aedes aegypti mosquito, can help to reduce the increasing problem of dengue and dengue hemorrhagic fever. Current vector control methods are simply not effective enough, and we're now facing an estimated 50 to 100 million new infections annually. Now, one promising method is to control the mosquito population by releasing sterile males, and this in turn will reduce the population in the next generation. This is known as the sterile insect technique, or SIT, and although it showed some very promising results back in the 70s, it's not being used in any large-scale programs today. Another technique is to introduce lethal or incapacitating traits into the females of the population, as it's the females who will bite and spread disease, and so that makes it particularly appealing. This new study is based on modifying a gene called the actin-4 gene in such a way as to render the female mosquitoes flightless. This gene is active in the pupal stage of the female mosquito, predominantly in an area called the indirect flight muscles, and the researchers created a modified insect where this gene is only properly expressed in the presence of a chemical called tetracycline, and this is through a method that they use to switch off genes called the TET-off system. In the absence of tetracycline, such as in the wild, these insects will reach maturity, but they then won't be able to fly. Now, allowing them to reach maturity unharmed is actually quite an important aspect of this. It means that the larvae can still develop, they can compete with other larvae that don't carry this mutation, and then only the adult female, that's the one that causes all the problems, is actually affected. It also means that rather than having to rear and release enormous swarms of these modified sterile males, we can transport, store, and release these modified eggs. Now, as the eggs can be stored and stockpiled, this means that any control program can actually start with a far bigger push than if we're relying on the maximum mosquito rearing capacity of any particular lab. The eggs will hatch, the females will be essentially killed off immediately because they're unable to feed, they're unable to avoid predators, and they can't find a mate. But the males will mate with the non-modified females, pass on this flightless mutation, so the next generation you'll have the same thing happening. The females will reach maturity and then immediately die off. And this should rapidly reduce the number of mosquitoes around to act as a vector for disease. They also say it might work with other species of mosquitoes, so this is definitely a very promising thing for us to be looking at.
And dengue is particularly problematic because we don't really have a treatment for it, let alone a way to prevent it, I don't think. But I can also see that people might get a bit upset about sending out these genetically modified insects into the world. So I guess we're going to have to be very sure that this works. But it's the kind of thing that's definitely going to be controversial at some stage, I imagine.
It probably will be. It's quite species specific. The males only mate with this species. So the likelihood of this modified gene actually getting out into other species is very unlikely. And as we've seen, it makes the females entirely useless. They cannot get around to breed anyway. So I suspect that it will probably turn out to be a very good thing.
I'm not anti-GM. There's better things to do with GM like this to deal with diseases than necessarily just feeding ourselves with a bit more food. Anyway, I'm going to take things back to the ocean, but back a long time into the past with some new fossil evidence that suggests that there were gigantic sharks lurking in Cretaceous seas around 90 million years ago. But these ones weren't terrifying monsters. They were in fact probably sluggish fish that sat around on the seafloor munching shellfish. Well, this isn't actually the first time that paleontologists have discovered fossilised parts of Dicodus mortoni, but new findings in Kansas in America reveal that these mysterious mysterious sharks went extinct at about the same time as dinosaurs, and they were probably much bigger and more slow-moving than previously thought. Now, based on fossilised teeth, scales and parts of the jaw, the team publishing in the journal Cretaceous Research, led by Keshnu Shimada of DePaul University in Chicago, Illinois, estimate that these sharks could have been over 10 metres in length. That's huge. That's bigger than 2 Humvees parked end to end, and it's bigger than the basking sharks that cruise our oceans today.
They're terrifying-looking creatures, basking sharks. I appreciate they're not particularly dangerous, but just the sheer size of them.
I think they're lovely, especially, and whale sharks, which are bigger still. They're all rather wonderful to think these huge fish are still in our oceans, but maybe even bigger ones used to be around as well. And the reason we think that they were probably slow-moving was from the shape of their scales, which were rather smoothed off, and other sharks that move quicker have actually pointed scales, which help to improve their swimming efficiency by reducing drag. And their flat plate-like teeth could have been perfect for crushing hard shellfish. And it's thought that these ancient sharks might have looked something similar to nurse sharks, which spend their time today lying around on the sea floor. And that does prove that not all sharks need to keep swimming to breathe, which is something that people commonly think but actually isn't true. And there's an even bigger shark, fossil shark teeth have been found from this same group, and that suggests that a closely related species to Tychodus mortoni could have been even more gigantic and perhaps was the biggest ever shellfish eater ever on Earth, which is a pretty fantastic record to have achieved. But just why these sharks were so enormous at this time, as well as many other creatures, in fact, were quite huge at the time in the sea. There were big clams and big fish. It all remains something of a lovely, enticing mystery.
It's amazing what we can learn from fossils, and you'd think that we can learn a lot about the physiology, about the shape these things are, but the fact that you can actually learn how they might have acted when they were alive, I think is incredible stuff. Thank you, Helen. And a big mystery is also what we're looking at whenever we look out of our own atmosphere and out to the Milky Way. We've discovered that 1/4 of the star clusters in our galaxy may, in fact, be aliens, according to a paper in Monthly Notices of the Royal Astronomical Society. The halo around our galaxy contains a number of clusters of stars, and these are called globular clusters, or GCs, and they orbit the centre of the galaxy. They tend to be more dense, a bit older, and contain more stars than the galactic clusters, which form the very familiar disk shape. Astronomers have known for a while that percentage of these GCs are alien in origin, captured as the Milky Way accreted dwarf galaxies, but estimating what proportion of these GCs are aliens has actually proven very difficult. Now, Terry Bridges, an astronomer at Queen's University in Kingston, Canada, and Duncan Forbes of Swinburne University of Technology in Australia, have used data from the Hubble telescope, among other sources, and compiled the largest ever high-quality database recording the age and chemical properties of these star clusters, and they've used this to estimate the proportion of aliens that are in our galaxy.
So how do you go about figuring out if there's aliens out there?
Well, there are a few dead giveaways. Firstly, you can observe how the clusters themselves move. Clusters that used to belong to a dwarf galaxy may retain some of its momentum after being swallowed by the Milky Way, and this will present itself in a distinct pattern, sometimes going the wrong way, orbiting around our galaxy. The second method is to use the metallicity of the cluster as a measure of its age. Now, metallicity can simply be thought of as the proportion of elements present in a star or in a star cluster that are not hydrogen or helium. Older clusters, or those with less activity, would be expected to have a lower metallicity, and this means that the relationship between metallicity and age can be used as an indicator for the history of any particular globular cluster. Bridges and Forbes discovered two distinct groups, one a fairly constant age of around 12.8 billion years, and one with a far wider range of ages. This younger strand is likely to consist of dwarf galaxies accreted by our galaxy in the last few billion years, and it accounts for hundreds of millions of stars, even as much as 25% of what we see in the halo of the galaxy. Astronomers have already confirmed that two dwarf galaxies, Sagittarius and Canis Major, have contributed globular clusters to the Milky Way, and these made up a significant proportion of the 93 clusters that they studied. However, even once these were removed from the equation, there's strong evidence that the remaining clusters originated from an additional 6 as yet unconfirmed dwarf galaxies. So, as always, space is enigmatic and fascinating, and there's still lots more to learn.
keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Helen Scales and Ben Valslow.
If you would like to contact us through Twitter, it's @NakedScientist. Just tweet with that in there and we'll pick it up. Or you can send an email to chris@thenakedscientists.com.
This week, we're looking at some of the scientific issues surrounding water, including how building a dam can change the local weather and how climate change looks set to affect water availability. First, though, the World Bank estimates that every year 32 billion cubic metres of clean water are lost through leaky pipes. And considering there are millions of people around the world without access to clean water at all, this seems incredibly wasteful. But there might be a solution. A Southampton-based company have come up with a leak-stopping system that really does hold water. We sent Mira St-Thillingham to find out how it works.
This week, I've come along to the head office of I2O Water in Southampton, a company that's main aim is to reduce water loss in urban environments, both here in the UK and globally. They've set about solving this problem by developing a new technology that monitors the pressure in the flow of our water supply. Here to tell me a bit more about this is the technical director here at I2O, Andrew Burrows.
Globally, water loss can vary between 15 and a massive 60% of the distribution water input. In UK, it's currently running at about 23% of the input lost as leakage.
Why is water lost in this way, and how difficult is it to control that?
Well, even with the latest technologies in water pipe work and network installations, the installation is always going to be a very complex network of pipes with many hundreds or thousands of connections between the individual pipes of the distribution network and also the connections for each individual property. So it's inevitable that there will always be a level of leakage in the network.
And now you've actually set about solving this problem by keeping an eye or controlling the water pressure through our pipes.
Yes, that's right. A significant influencer over leakage and also the frequency of bursts in the network is the pressure of the water in the network. Water pressure can affect burst frequency, so the likelihood of a burst occurring, of a new leak occurring, is related to the pressure, as you would expect. The rate of flow through an existing leak is also proportional to pressure. The higher the pressure, the higher the leakage through existing leaks.
So to set the scene a bit, how is our water distributed, say, from the main source of water to a residential area?
Water is typically sourced from either reservoirs, boreholes, abstraction from rivers or desalination plants. That water is then filtered and treated with chlorine. It's pumped into a trunk main system, which is running at a very high pressure. That trunk main system comprises very large diameter pipes that feed into the distribution network through meters and fixed outlet PRVs, which are pressure-reducing valves set at a fixed outlet pressure. That water then is distributed along pipes running down the roads with many hundreds and thousands of connections supplying water to each individual property.
Now, we've got a mock-up here in front of us, which has a pressure-reducing valve. It's about 1/2 metre in length, but above this, you've got a small black device which is connected to the pressure-reducing valve and is monitoring the pressure of the water before and after this valve. How does your system essentially work to control the pressure of water that's leaving this valve and reaching a distribution area?
The system comprises a controller, which is an electronic device which interfaces with a pressure-reducing valve, which controls the pressures in the district. There's also a remote sensor or remote sensors, which again are electronic devices monitoring pressures. These devices communicate over the internet to a centralized server. The server processes this data, learns the relationships between pressures and flows, and sends instructions back down to the controller. The controller uses these instructions to continuously adjust the pressure-reducing valve to vary the pressure constantly during the day to maintain the minimum possible optimum pressures in the network.
Within this controller itself, you have one also here opened apart. It's pretty complex in there. There's a modem in there, there's a battery. It looks extremely complicated.
The devices are really mini computers. The biggest challenge for us was energy, because these devices are fitted in chambers in the ground, in the roads. There's no opportunity to fit a solar cell, and we've got to run these devices for typically 5 years. So the devices have a key requirement for minimum power consumption. They're run from a single battery, which is roughly twice the size of a D-cell battery, and that device is then monitoring the pressures through piezo-resistive pressure sensing technology. The devices are recording the data and then connecting to the internet through the GPRS connection and transferring the data only when they need to. The control device also has to control the PRV through a special valve. The valve also requires minimum power consumption to make the changes.
What have been the results so far? So has there been a reduction in water loss?
In the UK, we're working with all of the major water companies now, and we're seeing an average leakage reduction of 20%. On a typical district metering area comprising, say, 2,000 properties, we're seeing reductions of around about 60 to 80 cubic metres per day.
Now, an important part of this, though, is that there are benefits that extend beyond simply controlling the water loss.
Yes, water distribution requires water to be pumped from the water source into the trunk mains. The pumping in the UK uses approximately 1% of the total electricity produced in the UK. So by reducing leakage, you're reducing the quantity of water to be pumped. So there is a significant impact on carbon being produced by those pumping stations. And also, we would be reducing the amount of chlorination required at the treatment works. Also, there'll be fewer bursts, which will reduce the social impact of repairing the bursts. So as you can see, controlling the pressure has a wide range of environmental benefits.
That was Andrew Burrows, Technical Director at I2O, explaining to Mira Sinthalingham how careful control of the water pressure in our pipes can lead to a dramatic reduction in the amount of water needlessly lost and wasted in urban water supplies.
Now, most of the water that we use comes from reservoirs, and these artificial lakes are often created by damming a river. Once a large enough body of water has accumulated, you can tap it off, purify it, and send it out to people's homes, or you can release it back through the dam through turbines to generate hydroelectric power. Simple as this sounds, though, there are environmental consequences, including an effect on the local weather. Dr. Faisal Hussain is from the Tennessee Technological University, and he joins us on the line now. Hello, Faisal.
Hello, Ben. Good afternoon.
Thank you very much. How many dams are there in the world? Do we actually know?
Getting a precise number is tough, but large dams, which are defined by the International Commission of Large Dams as more than 15 meters in height, there are probably about more than 100,000 of these around the world. And approximately, small and large, we might have about 1 million dams.
Right. 1 million dams sounds like an enormous amount. How long have they been around?
Most of them were built in the early 19th century, all the way up to, I think, right after the Second World War. And then in the 60s, I think, the environmental issues of it caught up, and most of them were built. So it stopped right around that time. So typical age is probably a few decades, maybe 2 to 3 decades or more.
That seems like fairly old for something that we rely on quite so much. Were they built to last?
Dams are generally built to last, you could say, almost forever, or if they're properly maintained and operated, you should be able to use the dam for what it was built for as long as you want. But there are issues with the dams, like it gets filled up with sedimentation and silt, and sometimes, dredging up the dam and all that gets a little hard, and it makes more sense not to use the dam or decommission or remove the dam from the river.
I'd imagine removing a dam is quite an engineering task as well.
Yes, it is. It's still not a very well understood discipline. It's just coming up because now we have to worry about what we're going to do with some of these dams that we built, and we really didn't think about what we're going to do in the first place when we built them, if they were not to last forever.
We can see fairly obviously that dams change the river flow in any particular river that they're put in. But what influence do they have on the local weather?
The first thing is it's a dam, it impounds a river and it creates an open body of water, which is an artificial reservoir or a lake. And that itself, being exposed to the sky and the sun, it creates a huge source for moisture in the air. That, as a quantity, may not be much, but if you factor in the other applications for which the dam is being built, in particular, like, say, irrigation, which, you're drawing the water from the dam, the reservoir, and then you're irrigating thousands and thousands of square miles or kilometers, and you're adding actually a tremendous amount of water vapor to the air. Thereby, you can actually change a lot of the dynamics of how the rainfall used to form in the pre-dam era. You can drastically change it to have perhaps more rainfall and much more heavier rainfall than normal.
So it's not just the building of the dam itself, but it's what you then go on to use the water for.
Yes, if you just look into the dam itself, that won't be much. You have to look into the changes in the landscape and the land use that it triggers. And most dams do, because a dam will typically make a region downstream safer from floods. So there's more urbanization, which again has impact on the weather. Then you can have more perhaps irrigation, more recreational issues. So you do change the landscape in a fairly drastic way, systematically. It doesn't happen overnight, but it happens on a scale of a few decades. And that in turn will lead to some significant changes in the local climate, depending on what kind of climate zone it is in.
This all seems very logical, that when you bung up a load of water and spread it out around the land, that you're going to end up with changes in the weather. But do we have any actual evidence that this is happening?
Actually, we do, because there were a lot of studies done by some of my colleagues that we're trying to work with now at University of Colorado, Dr. Roger Pielke, who's an expert on climate, and he and his colleagues have shown that actually irrigation, and particularly if you have a very heterogeneous landscape, you can actually increase the thunderstorm activity. In other words, you can make the thunderstorms more frequent, and you can make them much more heavier. So those short bursts of cloud water pouring in, you can make them much more extreme. So those studies have been there, but the connection to the dam and the reservoir as a triggering mechanism hasn't really been looked into from an engineering perspective.
And thinking of the engineering perspective, if building a dam does cause an increase in local rainfall, does this mean that actually the dams themselves have been designed for less water flow than we now get?
That is a possibility. Of course, the impact that a reservoir with its land use change creates is not uniform or consistent throughout the world. It's usually, you might see most of the impact in arid and semi-arid regions, as we are seeing in our research. And if they do change a lot of the rainfall patterns, and if you end up seeing more rainfall than normal for which was designed, yes, that together with the compounding problem of, increasing sedimentation or loss of storage can make the situation a little worse. In other words, you'll have more water coming in from upstream, but then every year you're losing a lot of storage in the dam, so it means you're actually having to keep the gates open more than what was designed for. So that is always a possibility.
Does that in turn mitigate some of the beneficial effects that you get, such as reducing flood risk? If actually you're keeping the gates open a large proportion of the time anyway, do you still get the floods that you would have got before the dam downstream?
I think it still does mitigate the big floods. Like, I'm a civil engineer by training, and by nature of my training, I am very much a pro-dam person. But as engineers, when we built the dams, we always treated all these design parameters for which we built the dam as static, as in, it's going to be the same 100 years down the road or 500 years down the road. But we never considered that the very structure that we're building and the applications that they're serving might itself compromise the design parameters. So yes, it may not be as successful or as effective as it was before for flood control, but it will still have some value. I think the key thing is to understand for which regions and what type of dams and land use these will be an issue, and kind of to modify our practice of operating the dams that's much more, climate friendly and much more sustainable in the 21st century.
With a better knowledge of the impact of building a dam, are we now in a position where we can predict a bit better what would happen if we were to build a dam or if we were to decommission one? And what sort of predictions could we actually make? Actually,
we are independently, the impact of human activities on the local weather has been going on since a few decades. So there's a rich body of research that's been done. People have looked into how urbanization affects local weather, how irrigation does, how other types of land use change. impacts, especially the rainfall. So I think we're poised at a very interesting time where we can connect all this to the dam building practices, and we've got excellent computer models that can actually predict the 50 or 100-year scenarios into the future of how the local weather might change. And I think this is what the civil engineering profession has to embrace to be able to, I think, do much better life cycle analysis, like throughout the entire lifespan, kind of predict the major extreme conditions and kind of plan for it in the design itself.
Well, I think that sounds like a very promising future for the future of dam design and dam building. That was Dr. Faisal Hussain. He's a researcher at Tennessee Technological University, where he's been looking at how dams alter the local weather. If you've got any questions for him, then do get in touch. Helen?
Yes, you can get in touch if you'd like to Twitter us. It's at Naked Scientists, or you can send us an email to chris@thenakedscientists.com.
Lifting the lab coat on the world's best science. The Naked Scientists.
This is The Naked Scientist with me, Ben Valsler, and with Helen Scales. Now, for many of us, a glass of clean water is literally just a turn of the tap away. But in many countries, millions of people still don't have access to safe water or sanitation. The death toll directly linked to this is 1.6 million people per year. This is not an insignificant fraction of people. One initiative that's been trying to tackle the problem in South Africa is the South African-based New Partnership for African Development, or NEPAD for short. Mira Senthalingam spoke to Eugene Kluter from the University of Stellenbosch, who chairs the executive committee heading the initiative.
NEPAD is an acronym for the New Partnership for African Development, which was formed to address a whole variety of issues on the African continent. It was decided that water science and technology would be one of the flagship programs. And the way that they organized this was to identify people working at research institutions and universities in the South African development community countries who have competence in the field of water research.
So what are the main aims of the NEPAD Water Initiative?
Well, first of all, it is to build capacity in terms of people that could go into government and people that also at the technical level could champion certain initiatives that will increase the sanitation situation, the water quality in terms of potable water guarantees, to improve conservation and the utilization of the continent's water resources, and then also to enlarge the range of technologies for water supply and improve access.
But how big a problem is water availability exactly in the southern African countries?
They have the saying in Africa that water comes in three forms: too much, too dirty, or too little. And all three of these are addressed by the NEPAD initiative. We can take a few countries here and we can look at, say, the urban and rural areas. If we take, for instance, a country like Mozambique, which has a population of around 20 million people, 47% of the people there have access to safe water in the urban area, and in rural areas only 40%. So it would be approximately 10 million people there that don't have access. If we go on to sanitation in Mozambique, the situation gets worse. Only 53% of the people living in urban areas have access to improved sanitation. This would be something like a flush toilet, while in rural areas only 15%.
So that's a high percentage of the population that don't have access to clean water and sanitation. But what are the actual causes of this? So what are the issues that need to be addressed in order to help provide access to this other 50%?
Well, first of all, where people live, the distribution of people, they live scattered very often over the countryside, where you have small villages where it would be very difficult in terms of economic considerations, but also very often practical considerations to pipe water to these communities. If they were living all together in an urban environment, it becomes a lot easier, and this is why we have much bigger access to safe water in urban environments. The other is purely the lack of knowledge on how to clean water so that it becomes potable for human consumption. It gets worse when you talk about sanitation, because if you rely on waterborne sanitation, you need a lot of water. Now, many, many people in Africa do not get their water coming out of the pipe. They do not have a flush toilet. They have to walk 4 to 5 kilometers a day to fetch water, and they will not use that water excepting for cooking, washing, and, drinking.
What is the initiative actually hoping to do then in order to tackle some of these issues?
We are looking at a whole range of projects at the moment. The one is looking seriously at rooftop rainwater harvesting. Because what that does is it brings the water to people in a decentralized fashion. So it's a new way of thinking about it, and there are a whole variety of different sanitation systems now which work with minimal water, which can then be used for irrigation, and that you could actually have a zero effluent system where people can grow their own vegetables and so on. That's one of the alternatives. I don't think going the way of providing pipes in all of the areas is feasible. Many of the people are not there on a permanent basis. They are basically living in shanty towns, and you don't necessarily want to entrench that by providing infrastructure there, but rather develop areas to which they can move with infrastructure. The second is to use technologies for disinfection purposes. For instance, the soda system developed in Switzerland, where you take water, put that into a plastic bottle, and you leave that out in the sun for a few hours, 2 to 3 hours, and that will sterilize the water. We have also got a project based on nanotechnology, for instance, where we have an in-the-bottle type filter containing activated carbon and nanobiocides, which then will provide safe water both from a chemical and a microbiological point of view. The application of that would have been, for instance, in Zimbabwe. About a year ago, there were 80,000 cases of cholera. All those cases could have been prevented if people knew about these low-key technologies which could make that water safe.
So it seems that there's small things that we can do that will make an enormously big difference. That was Eugene Kluter from the University of Stellenbosch. He was talking to Mira Senthilingam.
Now, another priority is for us to understand how people actually use water and how climate change and the way we use land can affect the availability of water in the future. Dr. Richard Harding is from the Centre for Ecology and Hydrology and one of the coordinators of the European network of researchers called WATCH, and that's short for Water, W-A-T, and Global Change. And he's with us now. Hello, Richard.
Hello, good evening.
Thanks for joining us on The Naked Scientist.
Hello.
Now, as we've just heard from Eugene Kluter, having clean fresh water is something that many of us take for granted, but it's certainly not the case that everywhere on the planet they have access to healthy, safe water. So what are the main problems linked to the availability of water and our uses of it?
Well, there's many problems linked to the uses of water, and we've heard a lot about them just now. But we have to realise that the majority of the water use that's used across the world is actually used for agriculture. Something like 90% of the water that is extracted in these dams and actually from the aquifers, the underground aquifers, are used for irrigating crops.
So 9 out of 10 litres of water we use is for food, essentially?
Yes, that's right. That's obviously an essential purpose, particularly at the moment we're having to feed something like 6 billion people. There are many, many people, particularly in developing countries, who don't have enough to eat. And in the future, we're going to have to feed perhaps 9 billion people by the mid-part of this century.
So we are looking at needing a lot more water to be able to feed all those people. So if water for agriculture is such an important and huge part of the global water cycle, if you like, is that what you at WATCH are focusing on?
Yes, what we're trying to do in WATCH is firstly to identify exactly how much water we have. And quite surprisingly, it's quite difficult to get a picture across all the world that we trust of what the rainfall is, what the evaporation is, and what the runoff in the rivers is. And then beyond that, we have to look at what the consumption patterns are now for agriculture, for domestic water use, for industry, and what they might be in the future and what the consequences of that might be.
And those are all things I assume that you're looking at, trying to collect more of that data and bring it all together.
Yes, what the WATCH programme is, and actually many of the researchers at the Centre of Ecology and Hydrology do, is we're trying to bring together the experts on the climate, the experts on hydrology who know about what happens to the water when it falls on the ground, and then there's another group of scientists, the water resource engineers, who understand how you store water, how the population uses water, and how it's supplied to where it's needed.
And we've talked already about agriculture, and I presume that as we change the way we use land and do different things with it, this must have a significant impact on water availability as well.
Yes, there's a lot of issues in that. Certainly different crops use water in a different way, and some crops use more water than other crops. And certainly as you change, for example, as natural vegetation is cut down and crops are put in, that again changes how much water is used. And referring back to the scientists from Colorado, that in itself has an impact on the local and actually the regional climate. So we have to take all these factors into account if we're to make a good assessment and a realistic assessment of how much water we'll need in the future and where we should be growing food.
And increasingly, many of us are living in huge cities, and presumably, as we heard already from South Africa, providing fresh water for all those people is a huge issue. And presumably, simply by building on the land and changing the way water behaves, we are also changing the availability of water for us to use elsewhere and in the cities.
Yes, we are. In fact, cities, the concrete of cities doesn't actually uses a lot less water than plants. So on one hand, by concreting over large areas of farmland, you're actually using less water, but there's a whole load of other issues. For example, the rainfall, particularly in areas where we have a very heavy rainfall, will run off city areas and concrete areas very quickly, and actually that water is sort of lost to the soils and the surrounding groundwater. So there are sort of pluses and minuses to the local water resources, and that's obviously before we consider the quality of the water that is in the cities and underneath the cities.
And we've already touched on the idea that we've got to feed lots of people, we've got to provide them with water, and that's already straining our current resources, and that's only likely to get worse as the population increases. And then we've got climate change as well to make things even more tricky. Is that something else, presumably, that you've got to take into account?
Yes, I think so. I mean, as you referred, there's actually many places in the world where we're already using water unsustainably, and there's many places in the world, for example, where the groundwater levels are dropping quite alarmingly because water's being pumped out to grow crops. In the future, the climate change is going to have an impact on that. We're actually quite uncertain about what rainfall patterns are going to be in the future. We're quite certain about that temperatures will increase, and that'll have an effect on increasing the amount of evaporation into the atmosphere. But it's much, much more difficult to predict what will happen to rainfall patterns. They're much more dependent on the patterns of depressions and circulations in the atmosphere. But there is general agreement from all the climate models that the dry areas are going to tend to get drier and the wet areas are going to get wetter. And of course that's pretty bad news, because dry areas like the Mediterranean, like the Midwest of the United States, like South Africa and Australia, are all predicted to get dry. Now, we're quite uncertain, so we're not absolutely certain about that, but it is looking that climate change will be an additional stress on what is already quite a serious situation.
Well, thanks, Richard. And just to finish things off, is Watch going to be providing solutions, or are you basically more handing your information on for someone else to come up with an idea of what we can do to increase the sustainability of water use?
Yeah, I'm afraid we're probably unlikely to provide many solutions. I mean, I think the solutions were very well summed up by your previous contributor from South Africa, who was essentially, in essence, saying that we have to use water much more efficiently, much more cleverly, and make best use of the resources we have. What Watch can do is give us our best estimate of what we have at the moment and what we're going to have in the future, which will sort of help us make plans and identify critical points and hotspots where we need perhaps to put additional resources in, maybe to build more dams, maybe to improve the distribution of water, or even maybe change the land use practices in some of those areas.
Thanks, Richard. That was Richard Harding from the Centre for Ecology and Hydrology.
Laying the facts bare. I say. The Naked Scientists.
You are listening to The Naked Scientists with me, Ben Valsler, and with Helen Scales. If you would like to contact us through Twitter, just tweet with @NakedScientists in it, or you can send an email to chris@thenakedscientists.com.
Right, well now it's time to join Dave Ansell for a watery experiment, and he's going to explain how water pressure dictates the shape of a dam.
In last week's Kitchen Science, which you can find online at thenakedscientist.com/kitchen science, Dave used water as a way to teach me about the processes that make wind. This week, we're looking at water itself, so I'm guessing, Dave, you're going to use the wind.
No, fundamentally I just like water, so we're going to use some more water.
Okay, well, it's raining out there, so it seems an appropriate day to be playing with water. What do we need to do this week?
Well, what you want is a big fizzy drinks bottle, a 2-litre plastic fizzy drinks bottle, a drill to make some holes in it, and a whole lot of water.
So if we're making holes in a plastic fizzy drinks bottle, I'm guessing we should have drank the fizzy drink first.
Yes, an empty bottle would be ideal for this experiment, otherwise it's going to get very messy.
Okay, and we have a drill. We're going to put holes in them just anywhere in the bottle.
Basically, you want a line of holes all the way up the side of the bottle. I'm putting mine about 3 centimetres apart. I'm going to start off with a 3mm drill, then open them out to about a 4.5, 5mm.
So this is one line going straight up the side of the bottle of reasonably large holes. We're certainly not talking pinholes.
No, you want something which water will flow out through quite nicely.
If you're going to do this at home, always be careful if you're drilling. Is there anything particularly dangerous about this setup, Dave?
Plastic lemonade bottles are very, very slippery, so you want to be particularly careful that your fingers aren't anywhere near where you're drilling.
Okay, I shall step back and let you drill in that case. So here we go with the first hole. Well, we now have a plastic bottle with several reasonably large holes in them. What's the next thing to do, Dave?
What we're going to do next is fill the bottle up with water and see how the water flows out through the holes. Now, the problem is the water's going to flow out from the holes as we fill it up. So first I'm going to put a piece of tape down over the holes, which will make it a bit easier to fill it up.
So we're just blocking the holes with tape before we go and fill it up.
I don't want my garage to get completely soaking wet, so let's go outside into the rain.
Well, it does seem appropriate that we're going to be standing and doing this experiment in the rain. And now we're just going to fill the bottle up from an outdoor tap. Let's get this done quickly, Dave. It's cold and I'm getting wet. Okay, well, it's clearly leaking a bit from around your tape. But what do we have to do now?
So I'm just going to pull the tape off and see what happens.
Well, very predictably, the water is coming out through the holes. But it's coming out quite a long way. It's squirting out a good couple of foot from the very bottom hole. The water level's so far down now that the top one is no longer anything coming out. But the higher up in the bottle the hole is, the shorter distance the water's actually going when it squirts out. What's going on there?
Well, water's a fluid, which means it's squidgy. So if you squash it from the top, it squidges out to the side, so it pushes on the side with the pressure. So the more weight there is above it, the harder it's going to push out on the sides. This means that the water at the bottom is going to be pushed out through the hole much harder than the water at the top. If you double the depth, that actually doubles the pressure, so it's going to come out with twice as much energy.
So if it's coming out with twice as much energy, it's going to go quite a lot further.
Well, the kinetic energy of an object is proportional to its velocity squared. So if the energy is twice as much, then the velocity is going to be the square root of 2 times as much, so about 1.4 times as much.
So it'll go about 1.4, 1.5 times further.
Yeah.
So even though there is only 2 litres of water here, we can already see a significant difference. I assume that this just scales upwards, and if we had a bottle twice the size, then we'd see that effect again.
That's right. Again, the bottom one would come out about 1.5 times further than it did from this.
So is this why when people build a dam, they make the base of it really, really wide, and then it just gets narrower towards the top?
Yeah, that's a lot of what's going on. It's also the reason why you want to build a high dam in the first place. Because for every kilogram of water which goes through your dam, if you've got 100 metres of water above you, that's going to be 100 times as much energy as if you've only got 1 metre above you.
Which is, of course, exactly what you want when you're generating electricity from a dam.
That's right, more energy per kilo of water.
Well, I'm starting to lose the feeling in my fingers, so this has been a very good but very cold Kitchen Science, and frankly, I'm getting quite wet, so I think we should go inside. That's all for Kitchen Science this week, and we'll be back with more very soon.
Well, for once, it's not me who's getting soaked in Kitchen Science. So that was the experiment showing us that a bottle with a line of holes can demonstrate how water pressure is much greater the deeper you go. So water squirts out much further from holes at the bottom of a bottle, and that explains why water at the top of a dam will leave with far less energy than it will at the bottom. And I can certainly vouch for how much pressure develops as you go down in the sea, because I spend quite a bit of my time underwater, and you can really feel the pressure building up just even 10 metres down. Your ears pop, and it really once you get to 40 metres, I don't recommend it, really hurts on your head. Anyway, for Kitchen Science, you can have a look at pictures and video on the website at thenakedscientist.com/kitchen science, and you can find out how to try all of our other experiments at home and watch videos of the dangerous ones that we really think you shouldn't try for yourselves.
Thank you very much, Helen. It does make a change that it's not you getting wet. Instead, it was Dave and I, which I guess we bring upon ourselves. We've had some feedback from you guys listening to the radio show or to the podcast. We had one from David Gould saying that he enjoys the podcast and would like us to keep up the good work. And he's in Dublin, but not the Dublin that you might be familiar with. He's actually in Dublin in California. No, I didn't know there was a Dublin in California.
You learn something new. That's great.
It's nice to know that people are listening in California. We also had an email from Joey Vega who said that it's such an interesting lineup of topics that we have. It means there's never a dull moment with us. And he also enjoys listening to British English, which I would have thought would be correct English. But he says 3 cheers for us, and I think we can echo him on that statement. We've also had another email from Michael who said he just wanted to drop us a quick note to praise our show. He himself is a chemical engineer and a patent attorney in Chicago, and he discovered the podcast listening to it on his mobile phone. He really enjoys it. He thinks we're very good at communicating complex stuff and keeping it simple. In particular, he seems to be very fond of Kat and her cancer research, so good on you, Kat.
All good stuff.
Now, Helen, we've had a question here from Philip Hill. He says, why do dolphins surf the bow wave of ships? Is it for fun or is it for food? And he explains why he got thinking about this. He said he was on a Brittany Ferries ship going out of Portsmouth, and there were lots of people whale watching, that sort of thing, and they were having presentations about it on board. So he asked the bloke on board whether they're definitely doing it just to show off and for fun, or if they're getting a bit of a speed boost to get them to another feeding site. So what do you think? Why are dolphins doing that?
Well, it's a wonderful thing to see for yourself. I remember the first time I saw a dolphin swimming in the bow wave and jumping into the air, and it was fantastic. And it's the sort of thing that's been observed way, way back in time. I think the ancient Greeks were telling us about dolphins on bow waves and things, so they've been doing it for ages, and it's the kind of thing that we don't actually know for sure why they do it. They certainly do get a power boost. They're surfing essentially the wave that the boat produces, and if any of you surf, you know how much power you can get from just sitting on a board and racing down a wave towards the beach, and that's essentially what dolphins are doing. There have been observations of dolphins doing this and maybe associating it also with fishing vessels, and they can come along and get some fish for themselves. That's one possibility. But then there's also been observations of dolphins riding a boat for miles and miles and miles and then just coming all the way straight back again after they've hitched this ride and then they return to where they came from. So that's clearly not going to be any energetic benefit from them. They might just be having fun, and they are deeply intelligent creatures, we know that. So why not just have some fun and hang out, and you can hear them talking and whistling to each other as they're going. I remember particularly wonderful, actually, later on in my research career when I was doing my PhD, I had the lucky time of going to work every day on a boat ride across a beautiful Emerald Lagoon. Are you with me? I hope so. And every morning, the same pod of spinner dolphins would join us, and I could recognise the patterns on them, and they'd come along and ride our bow wave on our way to our research site and leave us and then come back with us on the way back. So I do think there's a lot of fun involved, and occasionally maybe they are coming to feed, but we don't necessarily know, but they're up to something, and it's rather fun to be able to watch it.
They are very intelligent animals. We know they communicate with sound, but is there some truth that some of these jumps out of the water, some of what we think is of fun and dancing, is some of that actually communicative as well?
It could be. I mean, they do have very complex communications and very complex social groups. So it could well be that they're trying to say things to each other, and it's not all friendly as well. I hate to break the news that dolphins can be quite aggressive. So that's also a possibility. And all sorts of things for us still to discover about these wonderful creatures. We've also had a question here from Ron, who wants to know, rather relevant for today's show, how can I determine the direction of water flow through a pipe?
Well, Ron, I'm not sure if this is ever actually used for pipes, and it might be a bit more complicated than just tracing the pipe back to the pump itself. But you could borrow a technique that they use in medicine that relies on the Doppler effect. Now, you're probably familiar with the Doppler effect. It's what makes the sound of an ambulance or a police siren change as it's coming towards you or away from you. So when the source of the sound is coming towards you, the sound waves get squashed together, has a higher frequency, sounds higher. When it goes away, they're stretched, lower frequency, lower pitch. Now, you can also use this method in medicine with ultrasound, and in fact they use the ultrasound Doppler to observe blood flow in a fetus. And this is what we could steal to follow the water in your pipes. So if you put an ultrasound signal in at one end of the pipe, then if the recorded sound is of a higher pitch, then you can infer that it's been compressed by the water, and so that should mean the water's moving towards you, I think. So you could use it, but I think probably tracing it through to the pipes is considerably easier.
But give it a go, why not? Thanks for your question. Well, now it's time to find out an answer to our titillating question of the week with Diana O'Carroll. Hello, Diana.
Hello. Yes, this week there's no need for us all to be naked to show our bits because we can wear T-shirts.
This is John Gamble from Louisville, Kentucky, and I've had a burning question in the back of my mind when I went to a scientific meeting of ocular scientists down in Sarasota, Florida. There was this lovely young scientist from Budapest who forgot her bathing suit and put on shorts and a white T-shirt when she went swimming, and she was alarmed, and some of us not so alarmed, to discover that the T-shirt became virtually transparent as soon as it got wet. But she realized this, and she also was smart enough to hold the T-shirt away from her body. When she did that, it was no longer transparent, and I'm not really sure what the optics involved and why that happens. I'd be very interested if someone could offer an answer.
So, what's the physics that keeps the T-shirt competition in business?
Hi, my name is Professor Jeremy Baumberg, and I run a nanophotonics centre in Cambridge. Well, let's talk about the other way. How come we can't see through people's clothes? And there are two reasons for that. One of them is because we put dyes in them, which absorb certain colours of light and let other ones reflect back. But that's not true for white clothing, like cotton. So how come we can't always see through people's clothing, their underwear? And the reason is because clothes are made of fibres which scatter light. And they scatter light in exactly the same way that milk looks white. It's got tiny particles, called casein, which are about the same size as the wavelength of light, and light really strongly scatters against those particles into all directions, so we can't see through milk. So cotton is made of lots of fibres around the same size as the wavelength of light, and we can't see through it. When it gets wet, there's water around all those fibres, and then the light no longer gets scattered very strongly. So basically the material becomes more transparent.
But what about lifting the T-shirt away from the skin? Why should an extra layer of air make a difference?
So what's happening is that at each of the interfaces between the materials like the cotton and the water and the air, light is getting bounced, it gets scattered around. And so the fewer interfaces you have, then the less light gets scattered and the more you can see through it. So we might think of a nice experiment. How can we actually make clothes more transparent? Certain people might be interested in that. So you could imagine vapours with liquids which would absorb onto the cotton fibres. The fibres swell as well. That's also why the interfaces change. So you can imagine some very devious scientists deciding to really make clothes more transparent with the right spray.
That does sound like a very devious scientist looking to make clothes more transparent. I assure you, everybody at home, that this is not what scientists do in their lab.
Are you sure? So the Emperor's new clothes could come with a spray can, maybe. Light is scattered by dry fabric, but not so much by wet fabric, meaning you can see through it. When John's colleague lifted the T-shirt away from her skin, she was adding a layer of air in between her and the T-shirt, and it's this extra interface which will cause the light to scatter again, making it opaque. And you can see the same effect when paper gets grease on it, or when glass is dropped into oil and becomes invisible. Next week, we'll find out if money really does grow on trees.
Hi, it's Dominic from Newmarket. I'm just calling about how money is made and how the different colours are formed.
I want to know, how do they get that foil strip to go in and out of the paper? Help us to answer this question of the week by emailing chris@thenakedscientist.com or by writing your answer on the forum at thenakedscientist.com/forum.
Well, thank you very much, Diana. A very interesting answer and very, very small hints of smut inside, which I must admit I expected for a wet T-shirt based question. But that, I'm afraid, is all we have for this week. Next week, we'll be looking into the sun to find out the innovative new ways that researchers are using it for power and how nanotechnology can concentrate the sun onto solar panels for us. So if you've got any questions or comments for us, you can email us at chris@thenakedscientists.com or you can tweet @nakedscientists. We'll be back next week. Have a great week.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.